Hello and welcome to Living Proof, the joint podcast from the Isaac Newton Institute for Mathematical Sciences and plus.maths.org. I'm Rachel Thomas. There's many overlaps between mathematics and art. It's something people talk about a lot, and we've certainly reported on those shared ideas on Plus over the years, and also the Isaac Newton Institute, the INI, has had various programs on it too. But recently, this overlap was explored in a recent research program that happened at the INI. So last year, the INI hosted this program called Stochastic Systems for Anomalous Diffusion to explore some ideas in current mathematical research. But alongside the research program, there was a competition inviting artists working in a really wide range of media to submit work related to sort of the mathematical themes that were being explored in the research program. So two key themes that were being explored were things like randomness and the idea of diffusion. So diffusion is what you see when you pour some milk into a black coffee, and the milk diffuses through until the coffee and the milk are properly mixed together. Now, this diffusion process is down to sort of microscopic behaviour and random behaviour of the milk and coffee particles as they're interacting with each other. So the competition generated a huge amount of interest and some unbelievably impressive entries. So my colleague Marion Freiberger and our brilliant summer intern Ben Watkins talked to Codina Cotar, one of the organisers of the research programme and organiser of the competition, to find out about the mathematics, about the art, and about how they merged together. They started out by asking Codina to give us an overall sense of the sort of quality and range of entries they received.
There were many really absolutely fantastic entries, and they were showcasing lots of interactions of mathematics with other fields. There were entries which are trying to understand the mathematical phenomenon and put it in art and try to show the artist's representation of what the respective mathematic phenomenon was. There were entries from physics, from chemistry, from biology, which they had their own phenomena in the respected fields, and they were showing how, hey, this is just a phenomena coming from math, and this is what it looks like in art. And there were also many artists who some of them had already produced the art and had not realized that it was connected to mathematics until they had looked at the contest page, and they had looked at some of the themes that were appearing on the page and on the Newton program, and then they had read about it and they had realized it was connected to the art they had produced.
And could you give us a bit of an overview of how the competition worked, how many categories there were and so on?
So we had three main categories. So the first one was photograph, painting, film, print, animation, and videos, as long as they were not AI generated. Then there was textiles and sculptures and all other types of such art, so 3D printing, laser cutting, and then there were the AI or computer generated art, so which may have been photographs which were, for example, so enhanced somehow or had some, yeah. So there were three main categories. So these were with judges. We had a jury, and we had one winner in each of these three categories, a runner-up, and a third place. So there were 9 prizes in all for these categories. However, we wanted to also get the public involved. We wanted the public to give a verdict on who they liked, who they thought were their favorite entries. So with this in mind, we had 2 prizes which were given by the public. So we had an online vote, and the vote was for 45 days, and we had it set up so everybody could vote only once, so everybody could have only one unique vote, and we had over 20,000 votes.
That's amazing.
Wow.
Yes. Yeah.
And what about the jury? Who was in the jury?
So there were mathematicians in the jury, there were artists in the juries, there were people who were, so IT people who were working with AI and with computers. So we had a variety, and also just some people who were interested in art and mathematics, but were not experts in either of the fields. So we tried to have a combination of people. And we had a third vote, and this was just by the participants at the Newton program. So this was the 12th prize for £500 for who they thought. So these were people who knew all the mathematical themes, and we wanted them to vote for their favorite art entry, who they thought were best encapsulated the themes of the program.
Could you summarize briefly, in a kind of non-technical way, what are broadly the themes, the mathematical themes that people were supposed to have in mind when creating their work?
The first one was the one coming from probability theory, which was randomness. So, because this is what probability theory deals in randomness. And so people normally think that mathematics and probability theory are just these abstract ideas. Yeah, and however, what we really wanted to let people discover is that mathematics is not abstract, probability is not abstract. No, it's not something just disconnected from everyday life, that is all around us, that is somehow part of the fabric of life. We are surrounded by randomness, by order and disorder, by systems which interact with each other in seemingly anomalous way, which nonetheless give rise to quite universal phenomena or regular patterns, if you look at them through the right mathematical lenses. And there were two angles to this, yes? So we have mathematics, for which you have all these models, which sometimes can give rise to, you can simulate these models, and some of these simulations are really beautiful, breathtakingly beautiful, and they look like art. And at other times, as I already said, there's art which sometimes may be inspired by all what happens, by the randomness happening around us, by mathematics, sometimes even unknowingly, and some of the contestants discovered. And the Newton program, the Newton program that we had was in some sense ideally placed because to explore all these connections, because we had 6 workshops, and there were many themes at these workshops, many different mathematical themes at these workshops. So the underlying theme was diffusion, the theme of diffusion. So this refers to the movement of a particle or large object through space, which is subject to random effects. Yeah, and diffusion is a process which causes the interacting particles to mix because you have all these random collisions among themselves or with other particles. And in some sense, at the end result of diffusion is a fairly constant particle concentration through the environment. So at macroscopic level, what you would see particles which move from areas of low concentrations to areas of high concentrations.
So that's like when you drop your milk in the coffee, you will see diffuse, and in the end, everything has the same brown color.
We actually even had one of the entries was exploring this interaction of milk, and it gave rise to some really beautiful pictures. So this was the main theme. But however, diffusion has many interactions and many applications to lots of other fields. So there's applications to something to statistical mechanics. So this is a branch of physics which uses probability theory and statistics to connect the macroscopic behavior of particles to the microscopic behavior. And one really interesting thing that what you are trying to exploit in statistical mechanics is the so-called phenomenon of phase transition. So for example, you may have at macroscopic level, you may have, for example, water and ice, yeah? You see water and ice happening at 0 degrees, or water and vapor at 100 degrees. But there is a so-called phase transition between water and ice, and between water and vapor. This is what you try to model with probability theory at microscopic level, using the fact that what happens at microscopic level, you would have these interactions of atoms and molecules. Then there's quantum mechanics, which is also governed by probability theory. There's a lot, and then this feeds into things like material sciences. It feeds into things like sphere packing problems. There's also other fields there that you have connections to gas dynamics, financial models. There's a huge variety of topics that interact with probability theory.
So, should we move on to the entries? We can just talk about one or two of your favorites.
Oh, it's hard to pick a favorite, I have to tell you. I love so many of them. They're just so wonderful.
Okay.
So many
Well,
of them.
why don't we pick them, and then you don't have the hard work, and then we can pick one or two that we could talk about. Ben, is there one that you'd particularly like to talk about?
Yes, well, you were just talking about the beauty and the art of quantum mechanics, and I believe the winner of the section of that use AI and computer-generated art took on board this sort of beauty, right?
Yes, our lay. Yes, that was a really, really cool entry, and for me particularly, because I work in some of the topics of that entry. I was really enthusiastic when I saw it.
Can you roughly try to describe it to us? I mean, we'll include the video in the show notes, but can you give us a sense through words?
So the art was inspired by a model called the Sine-Gordon models. It rises in quantum mechanics.
So the artist uses that equation, and he has created a video. So you like that, Codina, because partly you were excited because that's something you work on. But what did you like about the art of this piece of art, like the artistic side?
Part of it, if you look at it carefully, in some sense, you can see that you have particles interacting in some sense with each other, and it's a very beautiful way of thinking of particle interactions and what happens in the long term as particles interact with each other, all the various phenomena that they give rise to, the deformations that happen. I really like this visualization of how particles interact with each other.
And it's amazing because it is very structured, but it's also quite complex.
Yes.
Yeah, so it's interesting, and it does a little dance. I mean, it literally does a dance. This one, it's almost psychedelic.
Yeah.
So this is an example of something where somebody actually took an equation and visualized it in some way. So obviously that is very much related to the math. There was an entry that I found quite interesting, which involved dance. That was the runner-up in the public vote, Mariam Tahiri.
Oh yes, that was wonderful. I particularly like that entry because it was a classic example of some of the themes in probability theory, like for example, random walks. Sometimes if you try to explain to somebody from the street what random walk is, it may not always be very easy to explain to them what a random walk is. But if you look at the entry that of Miriam, you can see the visualization of how random paths happen. It explores not just random paths, but other potential paths which didn't happen and could have happened. And what happens if you take a particular the consequences of taking some paths, but not others.
You see people moving, you see people dancing, but you also see them kind of fade away like ghosts. So this sense of what is happening and what could happen is sort of embodied in that.
Yes.
But it made me think of something. I recently talked to two people. They're actually working on a project for primary school children, which is meant to get, because the mathematician of this couple is an epidemiologist, and they are working on dance activities that will introduce children to the idea of contact networks.
Oh, yeah.
So this is really cool. So I was wondering, do you think that these kind of approaches could or should be integrated into the way people come across and learn mathematics, like say at school or something. Is there a way of bringing art into the way that maths is taught that would be constructive and useful?
I think so. I think so, because it's important in some sense to humanize mathematics and that people realize just how connected mathematics is to everything around us, rather than just some scary topic. Most of the time when I talk to people and they ask me what I do, they say, "Oh, mathematics always scared me, so I never learned it when I was in school." I think for a lot of people it's a scary concept, and it's important to let them know since they are children that it's not a scary concept. So my father loved mathematics, and when I was small, he tried to teach mathematics to me since I was a small child. And it was through, since I was very small, he would tell me, "Your nose is a triangle. Your eyes are like circles, Cody." So he would try to show everything around me through mathematics to try it, and it was not something scary. It was something I really enjoyed, because he introduced it through play, through examples of everything happening around me. So I started loving it. So I think it's very important to introduce mathematics to kids in a way that they can associate with the world around them through play, through art, so that they can see it's something fun, it's something beautiful, and that it's something that it expresses the whole universe in some sense.
And it's rhythmic, right? I mean, mathematics,
Yeah.
so much, the structures have so much rhythm to them. So the idea of movement is quite natural.
Yes, it is.
Talking about like the rhythm of movement, I quite liked Lilia Bakanova's piece. It's all about sort of boundary layers and like fluid mechanics. I think particularly looking at the Aral Sea in Central Asia. Do you want to talk about that?
This sea, which is really a lake, it vanished due to Soviet irrigation project, but it left behind these kind of physical traces like ripples, sediments, and salt. So this piece of art, which is fabric, it sort of tries to recreate these physical traces left in the sea, which again they're created by smaller components interacting with each other.
So what I really liked about this entry, that it connects to some of the other applications of probability theory, for example, in material sciences, and the way that randomness gives rise to quite some nice structured phenomena in some sense. It gives rise to surfaces which have some structured, beautiful behavior, and you may see this behavior at microscopic level, but you may not understand why what has caused this at microscopic level. So this is a very beautiful example of that.
So what is going to happen? Like, have the winners already received their prizes? Like, did you have a ceremony or a celebration?
So the prizes have been announced. So we are now in the process of them receiving the prizes. So the monetary prizes, so to speak.
And I mean, this was a great success, right? Because you had so many entries. How many entries did you have?
So we had 528 eligible entries. And out of these, we selected 323 for the web page. So we put them on the page. And out of these, so the jury had made a long list, and the long list had 150 people on it. And then out of this long list, they selected the finalists and then the winners, and there were really many wonderful entries, and I had many favorites. And I have to say that I was sad, really sad we could only have 30 finalists, and that we could only give 12 prizes, because there were many really cool entries which didn't make it among the finalists. And out of the finalists, it was really hard to pick in some sense.
Are you going to do it again? Are you gonna run another competition? Because this seems to have been a great success. Also with the big, the participation in the public vote being 20,000. That's huge. So are you going to do it again?
Yes, hopefully, but maybe in a couple of years, because it was a really huge amount of work to organize all of this. And I think, yeah, but I mean, in the long run, it would be nice to have a regular event. I mean, this is the goal, to have a regular event. So, for example, if you look at the American Mathematical Society, they try to organize a regular event for mathematics and interaction with art, and they do it in some of their conferences. They showcase some of the artists in some of the really big annual conferences that they organize. And in the UK there is nothing like this happening, and it really would be nice if we could showcase some of the interaction between mathematics and art in some of the major conferences that we organize here in the UK. And it really would be nice to have a regular event. So I'd like to try and see if we can start something like this in the long run.
The idea of having such a regular exhibition in this country sounds fantastic, and we really hope that the mathematical forces here in the UK join together to make that happen. You can see the artworks that we've mentioned in the podcast today in the show notes for this episode, and we'll also include links there for you to find out more about some of the art and the mathematics that we've discussed. For those of you in Cambridge or who can make it to Cambridge, there'll be an exhibition featuring some of the winners at the INI at the end of September or the beginning of October. So keep an eye out for the dates for that on plus.maths.org or on the INI website. You can also find out more about the competition in articles that are planned in the Chalk Dust magazine, and also a special volume that's going to be published by the London Mathematical Society. So we hope you've enjoyed this chance to explore the connections between maths and art, and the fantastic way they've been explored through this programme at the INI. Thanks very much for listening, and bye for now.